Okay, so let's get started. Last 2 weeks of this semester. So first half of this class, we are gonna talk about heap exploitation. After that, we're actually moving down. We are moving to the micro-architectural level. We're going to talk about how CPU cache works and how cache side channel attack works, which has been a super hot topic in the last 20 years, I would say. But for the last 5-6 years, there has been some very important advancement in that area, breaking systems that we thought are secure for decades. We find new way to break them. However, that part, the cache side channel attack part, will not be in the final. So the final will only cover what we teach the first half of this class. So next class, today we were talking about the basic idea of a cache, how cache side channel attack works. The next class we will talk about two particular attacks. One is called meltdown, one is called spectral. Then we're going to review the whole class and talk about the future, about software security, and we are going to watch a video together as well, talking about the future of software security. So it's time for class evaluation, same as the midterm evaluation. If 90% of you submit evaluation, then everyone gets 10 bonus points. And also, how many of you have started working on ROB 2? Okay. Anyone get the flag so far? No? Okay. So I don't have a working exploit right now. I had one at some point, but I cannot find it. So because of that, some of you came to my office today, and I couldn't explain how it works. And because of that, tonight I'm going to work out an exploit. I think now I recollected my memory how it works, but redevelop that may take some time. Because of that, I will give you guys an extension for this homework. And also, after I finish that tonight, I will give you some hints on how to do that. This is possible. Last semester, last year, 12 students actually got the flag. 12 students, probably out of 50, they actually got the flag in the homework. So it's possible, okay. When we were looking at the code an hour ago, somehow I thought, oh, this is not solvable. Then I thought maybe I updated the system, making it unsolvable, but it's not the case. Okay, so today we keep talking about heap-based buffer overflow. Last week we talked about, at a high level, how heap works. And heap-based buffer overflow basically works the same as the stack-based buffer overflow. However, on heap, we don't have something like a cookie or calorie to protect that, because there is no point, like there's a return, so we can check that. And in the real world, a lot of very cool and complex things, they use very complicated structures like browser, very complicated software. You can consider browser as an OS for web applications. Very complicated software, and you have to use heap to develop those kind of software. And a lot of object structures, they stored on the heap, not on the stack. It is also very common to put function pointers in those structures. And we already know that function pointer is basically a code pointer. It's the same as a return address on the stack. Those are very dangerous because they decide the control flow of the CPU, decide where CPU continues executing code. If you can override function pointer, attacker can override a function pointer, the attacker may execute arbitrary code on the computer. So we have two examples for heap exploitation. The first one, still very simple example. We have one structure called airplane. So this is a C structure, but the structure of this looks a little bit like a C++ structure. A C++ structure, usually at the very beginning, you have a virtual function table. And on that virtual function table, there are many function addresses. So here we have what? We have one function pointer, and that function's prototype is just returns void, and it doesn't take any parameter. And this one is a function pointer. After that, we have an array of 20 bytes of characters. So that's the airplane structure. And we define a function called fly. And the function doesn't do much, just print out flying. That's it. Then in the main function, we first print out where that fly function is. And also, in this address space, we have the print flag function. We print out the address of both functions, fly and print flag. Then we create two airplane structures here. The first one, we use malloc to create that. We malloc the size of airplane. Then we print out the address of that airplane 1. After that, we create airplane 2. Also print out the address of that airplane 2. Then we just set the function pointer for both structure to the fly function. Okay? So before that, the fly function, the pointer, the function pointer pfung, will point to some random address because this is on heap. It's not initialized. We set both of them to fly. After that, we call fgets twice. And this is where the buffer overflow happens. The first fget take 10 bytes from stdin and put in airplane 2's name. And airplane 2, the name has 20 bytes. So this is not going to cause any damage. No buffer overflow the first time. However, the second line, fgets will put 50 bytes from stdin to the first airplane's name. However, the first airplane, the name also 20 bytes, and because of that, there will be an overflow, right? So this overflow, let's say this is a structure of airplane 1. This overflow is not going to overflow airplane 1's function pointer because airplane 1's function pointer has a lower address than its name. Okay, at SQL level, this appears first, then the name. So usually compiler will put this pointer first, then the name. However, those two structures, they may be adjacent. So you can actually overflow airplane 2's function name as well. So after that, we will call the airplane 1's pfunc and airplane 2's pfunc, then free both of them. So if there is no overflow, there is no attack, we go to heap. Heap overflow 1. So if there is no attack, heap. We run this program, we give some input, 2 inputs, right? Then it will print out the flying function is at this address, the print flag function is at this address, the airplane 1 is on heap, it's at 5B0, and the airplane 1's name is at this address, B0 and B4. So you can see that the whole structure, the first element is the function pointer, the second element is the name. That's why the first element of the address is that structure's address, which it is at 5B0. However, the name's address is 4 bytes higher, 5B4. Then airplane 2 is at 5D0, which is at an address higher than the airplane's address. Then you give it 2 input. The first input becomes the name of airplane 2. The second input becomes the name of airplane 1. Since we didn't overflow anything, so 2 planes, they just flying there. So if we run this again and we give much more input, let's say the first one, we give a very long input, then actually, because the first here, the fget takes 10 bytes, then the rest of it will go to the second fgets. So you can see, by doing this, we overflow the airplane 1's flying function. So we only got one flying here, that's airplane 2's flying, and airplane 1, we only get a segment fault. Okay. So how do we get the flag of this one? Looks like quite simple, right? So we only need to overflow airplane 2's this function pointer. That's it. So we can do a little bit calculation here to say how many bytes we need. So both of them are on the heap. And the airplane 1 is created first. So we have airplane 1. And from last class, we already know that the malloc chunk has some metadata. And here the metadata has previous chunk size, current chunk size, both of them 4 bytes on a 32-bit machine. So 8 bytes here. Then a function pointer, which is 4 bytes, name 20 bytes. Now after that, if there is, maybe they are just adjacent to each other. If they are adjacent to each other, then after that, there will be airplane 2's previous size, function, and name. Since we already print out those addresses, you can calculate their distance. So the exploit will just look like something this. Very simple. First, you will print out, you will give the name of airplane 1, and it take at most 10 bytes. You give it a new line, then you will consider taking whatever is before the new line. Then after that, we actually need 28 bytes to overflow this part. The airplane 1's name, 20 bytes, and the metadata of airplane 2, that's 28 bytes. Then after that, we will have airplane 2's function pointer. Then we just put the function pointer there. That's it. Very simple. So let's see if it works. So first we need 28 bytes of garbage. We first need a name for airplane 1. So like this, we need a new line there. Then new line is a /n. After that, we have 28 bytes of garbage. Then after that, we just have the address of the printf function, which is cd 62 5556. Pipe this into the program. So you can see that. So this is how we overflowed airplane 2's function pointer. Obviously, if this is changed, it's not going to work. Oops. So that's how we flow something on the heap. Okay, this part is easy. Then let's keep talking about more complicated cases for heap exploitation. And one class of heap exploitation is called use after free. So the previous example we saw, it's not use after free. So both objects, they are still in use. We overwrite one of them. So next we are going to talk about some of the objects are not in use anymore. However, there is still a pointer point to that object, and that pointer is called a diagonal pointer. And this has been a very popular vulnerabilities issues in Nudge software. The reason is, as a developer, to correctly use heap, you need to do malloc correctly. You also need to do free correctly. When there are multiple threads, many threads, concurrency makes managing those heap objects very complicated. And developers makes all kinds of mistakes. So the use after free vulnerability is actually among the top 10 computer CWE is called Common Weakness Enumeration. So this is a list created by MITRE to list the common software issues. And you can see that use after free is in top 10, it's number 7. And that buffer overflow technically is out of bounds right. So it was ranked number 1 last year. Then the second and the third, you can see they are actually web-based. The second one is called cross-site scripting. It's not related to binary software. It's about web, especially web script. The third one is secure injection. Also, there is out-of-bound read. So use after free is a very popular vulnerability. So how does use after free attack works? On the left-hand side, we have the address space of a program. The program has stack, has heap. The top is lower memory. The bottom is higher memory. Then on the stack, we may have some pointers, right? And then on the heap, we have all kinds of objects. And the objects on the heap are created by malloc. However, the pointer on stack or the pointer on global variable, they may point to the objects on the heap. In this figure, we have 3 heap objects. So all of them look like this. There is a previous chunk size, current chunk size, and the data part. And we know that the pointer will point to the data part. The pointer doesn't directly point to the previous chunk size or chunk size. However, there is a constant offset. So as long as you know where the buffer is, the data is, you know where the previous chunk and current chunk size is. So you can malloc 3 objects on the heap. Then you need the program may free 2 chunks here. Now those 2 chunks becomes invalid. We don't know what is there. However, the developer may forgot to update the pointer. The pointer still points to there, and it's still a valid pointer. So in C programming book, the book tells you that if you free an object, then you need to set the pointer to 0. To set the pointer to null. But most of the programmers, as long as you ask a programmer to do something correctly, they are not going to do that, right? So that's why this problem happens. And those pointers, when they point to objects that do not exist anymore, we call those pointers dangling pointers. So they are pointing to some valid address. However, there is no guarantees on what data is at that address. This is also called a stale pointer, a while pointer, and this happens in all kinds of complicated software, like the browsers, also like the Linux kernel. Of course, the kernel doesn't use a usernet heap. The kernel has its own kernel heap, but it's implemented in a similar way and has similar issues. So a lot of kernel exploit right now relies on those kind of a kernel heap exploitation. So actually, one of our projects right now is using a new hardware feature called pointer authentication code to help solve this issue. So let's say this example. Previously, we freed this part, but now we call malloc again. So this region of memory is reused. However, after we reused this region of memory, we put some new object, new structure there. It is not guaranteed to be the same as the previous structure. And that is where the problem is, because the diagonal pointer still points to that and can still be used. So to exploit the use after free vulnerability, you usually, attacker, have to allocate a different type of object over the one the system just freed. Now let's take a look at the second example. Now we have two object types in this program. We have airplane, which is the same as the previous airplane, which has a function pointer and a name. Then we have a different structure called car. The car has a volume, then also has a name. So those two structures, actually, they have the same size, because the volume is also just 4 bytes. The pointer is 4 bytes. They have the same size, but they are different structure. There is a flying function. In the main function, we print out flying and print flag. After that, we first create an airplane object on the heap using malloc. So malloc, this interface doesn't really care what structure you create. It only asks for the size of the structure. So we just say the size of an airplane. Then the pointer, the pointer type is still a structure airplane, and this is developer defined. After that, we set the p fun to fly. Then we call this function. So when we call this function, obviously that airplane will fly, right? The interesting part here is now we are going to free this malloc chunk. We are going to free this object airplane by calling free p here. So the correct usage, correct practice after this is you should set p equal to assign 0 to p, right? That's what the textbook tells you to do. But no one does that. Okay. So after this, you should set p to 0. Now we have a different structure. We have a p1. So after the free, the p is not changed. P still points to that address. Now we have created another structure, which is a car. We use malloc to do that. And this car will actually be placed at the same place where the airplane was placed. So for most heap implementations, it will do this thing. Okay, it doesn't add another layer of randomness. Of course, if you add another randomness, it will be slower. However, it will be a little bit more secure. So now we will print out where the car is. So later you will say that the car and the airplane, they were placed at the same place. Of course, not at the same time, but at the same place. That's why this kind of issues are also called the temporal issues, because it's like two different objects are sharing at the same memory region at different time. Then after that, we set a volume and ask you to input what is the volume of the car. Then use scanf to input the volume. Then we just set the volume. So here is the interesting thing is the pointer P is still here. And pointer P has a prototype of airplane. It's the pointer we had at the very beginning of the program. It's an airplane pointer. Since it's an airplane pointer, you can use that to call airplane's member functions. In this case, there is a function pointer. So you can still call this function, even though what on heap in that same memory region is not guaranteed to be an airplane anymore, right? So this is a C program issue. Then after that, you freeze this. So if we run this program, oops. If you run this program, it print out fly is at this address, printf is at this address. To make it convenient for you, I just print out the decimal here instead of hex. Then airplane is at 5B0. Then after that, the airplane is freed, right? However, the pointer is not updated. So then the car is created. However, you can see the car is created at the same address airplane was at. So after that, you can input the value of the car. So the value of the car will be at the same address as airplane's function pointer, which means if you put some random value here, then that value will be treated as an address of a function, and the control will go there. So if we do this, obviously we will get a segment fault. However, if you put the address of the print flag there, like this, then you input this as the value of the car. However, this statement pfunc will treat whatever you input as a cost volume as the address for this function. Then we'll call that function. And that function is a print flag. So when we do this, we will get a flag. Okay, so that is how it works. So that is one way to exploit use after free. There are actually more advanced ways to exploit this, and we are going to see two more examples. However, we are not going to do that in the final. So you are already familiar with the malloc chunk data structure. It's basically there are 4 bytes of metadata, previous size and size. However, the metadata is always there, whether this chunk is in use or it's freed. However, if the chunk is freed, there are actually 2 more piece of metadata there. One is a malloc chunk star forward pointer, and another one is a backward pointer. So basically, all those freed malloc chunks, they are chained together using a double link. That's the original design. We actually find that many of the recent designs, they do not necessarily chain them as a double link, but still they connect them together, maintain them in a link, but not necessarily a double link. So in most heap implementations, when you free an object, the heap manager will try to consolidate some nearby chunks together, basically merge them together into bigger chunks. And that is a default operation for a lot of heap implementations. This figure you actually saw before last week, but now we are going to use this to explain a different case. So we have 3 chunks here. They are adjacent to each other. Chunk A has a previous size, current size, user data, and chunk A is going to be freed in this case. Chunk B is already freed. It's not in use. So which means chunk B has 4 pieces of metadata, which is previous size, current size, and also previous in-use bit. In this case, this bit is 1 because the previous chunk A, is still in use. Then it has a forward pointer and a backward pointer. Then it has the used to be the data part. Right now we're not using that, so it's unused. Then we also have chunk C. Chunk C is in use. So it has previous size, current size. In its current size, there is previous in use. Its previous one is chunk B, which is not in use. That's why that bit is 0. Then we have data. So now we're going to, so B is freed, C is used, and A is freed. A is being freed. So some of the heap managers, memory management systems, will try to consolidate A and B together to make it a bigger chunk, right? So this is to avoid memory fragmentation. So if the developer asks for bigger memories, we still have bigger chunks available for them. Otherwise, we may get smaller chunks, and get a lot of fragmentation and never be able to reclaim bigger memory regions. So in this case, let's assume that chunk A will be consolidated with chunk B. Then some of the existing implementations work like this. We have 3 chunks. So those are all freed chunks. Okay. So there is a header of that double link. Many of the implementations don't look like this anymore, but in the textbook, it looks like this. This is bin itself. It's like the header of this double link. Then the header of the double link has a forward pointer, point to a chunk 3, which is a freed chunk. Chunk 3 point to chunk 2, another free chunk, point to chunk 1, then point to the bin itself. Also, there is a backward link. Chunk 3 backward link to bin, bin backward link to chunk 1, chunk 2, and chunk 3. So in the malloc, the DL malloc library, actually we have we saw several macros to look for next free chunk or previous chunk, and those are the pointers we found there. Then they provide an unlink function to free a chunk from a bin. This is how the unlink function defined in most libraries. And this is not really a function. If you are familiar with C, this is just a macro. So the unlink is a macro, and this macro has vulnerabilities. And this is a library implementation, and we're going to look at this and say why it has vulnerabilities. The unlink, let me just call it function. The unlink function takes 3 parameters. One is P. The P basically is one chunk's address. Then it takes a backward chunks address and a forward chunks address as input. And it does 4 things, just the 4 steps. So before we do this, let's say this is what the memory looks like. We have chunk 1, chunk P, and chunk 3. Chunk 1's forward points to chunk P. So chunk 1's forward pointer, so all of them are freed, okay? Then chunk 1's forward pointer points to chunk P's address, which is chunk P's previous size address. Then chunk P's forward points to the next freed chunk, which is chunk 3 here. Then chunk 3's backward points to chunk P's address, and the chunk P's backward points to chunk 1's address. So all of them are free, that's why freed. That's why they have the forward and backward. Now, let's say step by step how those 4 lines work. The first step is we set a backward pointer as the chunk P's backward pointer. Okay? So chunk P's backward pointer supposed to point to chunk 1's address. So now we set the backward pointer here. Now we set the forward pointer. The idea here is we are going to remove this chunk out of this double link. Then we set the forward pointer as the chunk P's forward pointer. Then the third step, the forward pointer's backward pointer will point to the back pointer. So the goal of this, so I don't know if in data structure class you implemented a double link before. So this is basically how you implement a double link and remove an item from a double link. So now, chunk 3's backward does not point to chunk P anymore. Instead, chunk 3's backward points to chunk 1. Chunk 1's forward doesn't point to chunk P anymore, it points to chunk 3. So after this, basically, this chunk P is not in this double link anymore. So that's a goal. So then we will be able to use chunk P. However, the problem here is how do you change the pointers and what is the value you change determined by the chunk itself, right? It's related to the chunk's own data, like chunk BP, its backward pointer and forward pointer. It's related to that. But the data here, you cannot really trust that. The data could have been overwritten by the attackers. So let's say you're an attacker. Before this unlink function is called, which is a library function, before that is called, you overflow what is in this backward pointer and forward pointer. They are supposed to have some legit value maintained by the library, by the memory manager. However, you can overflow that. If you overflow that, you will be able to do arbitrary write here, actually. So you can do 2 writes here. And this is basically the equation for that. You can overwrite 4 bytes twice to 2 different locations you choose. So that's basically the unlink attack. Okay, so also there is a free attack, but let's say. So the free function, we already know that free 0 doesn't really do anything. And also for the malloc chunks, you can use malloc to allocate them. You can also use memory map to allocate them. So if it's allocated using memory map, you are supposed to use memory unmap to do that. And the memory map, memory unmap, they allocate bigger memories, even though technically they are still on the heap. However, memory map, memory unmap, they are system calls. So OS will do something for you. But if you do malloc free, they're just function calls to the C library. So only large chunks are supposed to be memory mapped. And in this class, we don't really talk about that. So if a returned chunk borders the current high end of the memory, it will be consolidated into the memory higher than that. And if the total unused topmost memory exceeds the trim threshold, a malloc trim function will be called. So that's how most of the memory manager implemented. So other chunks, they are consolidated as arrive and placed in corresponding pins. If no adjacent chunks are freed, then the freed chunks is simply linked into corresponding bins. Use a forward link function, a front link function. If the chunk next in the memory to the freed one is freed, and if the next chunk borders on the wideness, then both of them are consolidated with that bigger chunk. And many different issues there. Let's say the same example here. We have chunk A, we have chunk B. Then, because chunk A is at a lower address, chunk B is at a higher address, then it's possible that there is a buffer overflow, like we just saw in our first example. So when we overwrite chunk A's user data, it's possible that we overwrite chunk B's metadata and also chunk B's user data, right? Then, since we can overwrite chunk B's metadata and also user data, we can actually create a fake chunk at this place. We can create a chunk that doesn't exist. We can create a fake metadata. We can create fake pointers. We can make them look like they are freed. Then after that, so for example here, we can create two fake free chunks. Since now they are free chunks, later with the unlink, use them, it will use the data here to overwrite some other places. I don't really have examples for that. This is very implementation specific. Some of the libraries, they were implemented differently, but in general, this problem exists. So that's basically where we stop for software vulnerabilities for this class. And now we are moving to a new topic, and also very interesting topic. It's not really at the software layer. However, the software layer can exploit this vulnerability. And that's the cache side channel attack. Today we will talk about side channel attack, and the next class we talk about meltdown and spectral, two infamous and famous attacks discovered maybe 5 years ago, 6 years ago. So, first of all, what is cache and why do we need a cache? So in the last 40 years, the speed gap between the CPU and our main memory is actually getting bigger and bigger. Our CPU is very fast. However, well, both of them are getting faster, but CPU is even faster than DRAM. So most of our system we use, the main memory we use is DRAM because DRAM is very affordable. The CPU itself doesn't have DRAM. It has something called SRAM. DRAM is dynamic RAM. You need to keep refreshing the cells. However, SRAM, you don't need to keep refreshing them, and the SRAM is super fast. So the registers, they probably is actually manufactured using the same thing as SRAM. And cache, the CPU cache, is part of the CPU, and it's SRAM, and it's very fast. Some of the low-end devices, like a lot of microcontrollers our lab use, they do not really have DRAM. They only have a very small SRAM. So because there is a huge gap between the CPU and the main memory, we want to create something in between. Basically, this is a trade-off between speed, cost, and capacity. We cannot get something super fast, super cheap, and with huge capacity. We don't have such a thing, right? So what we usually have is, let's say we have hard disk, which is very slow, but the cost is very low. The capacity is very high. We can easily get 2 TB with just hundreds of bucks right now. Even SSD, it's relatively cheap. Then we have something like a DRAM, which is relatively fast, not that expensive. Capacity is okay, right? Your laptop right now probably have like 32 gigabytes of DRAM. That's memory part. Maybe some of you have like bigger 64 gigabyte, but usually not bigger than that. Then you have the CPU, SRAM, super fast, super expensive. The capacity is very small. Usually for your CPU, your cache right now could be 128 megabytes. That would be a very powerful CPU. Then the registers, we already say that for 32-bit version, the entire CPU, there are only, you saw that general registers, only 8 general registers. Each of them is 32 bits. That's very, very small, but they're very fast. Then for 64-bit version, you have more general registers, maybe 20-something, but still, compared to your hard disk, compared to your DRAM, they are still very, very small, right? But fast. So CPU cache is a small amount of very fast memory, usually built by SRAM, and that cache goes between the CPU and the main memory. It's part of the CPU. Technically, it goes between the register and the main memory. And it keeps a copy of the most frequently used data from the memory. And there could be multiple layers of caches in modern CPU. This is a data from 10 years ago. If you access some data in a cache, move data from cache to register, it takes 0.5 or 2.5 nanoseconds to do that. If you take data from the DRAM, main memory, to register, it could take 70 nanoseconds. If you take from your hard disk or flash, it could be 50,000 or even 20 million nanoseconds. So the speed, you can see the huge difference between the speed. However, like we said, the cache is very small. Your hard disk has 2 TB. Your cache is only 2 megabytes, maybe bigger than that, 4 megabytes. Very powerful servers, I say something like 128 megabytes. I haven't seen something like a 1 GB of cache yet. So because the size difference, which means obviously you cannot put everything in your hard disk in your cache. So if the data you are looking for is already in the cache, then we call this a cache hit. Otherwise, we call it a cache miss. If it's a cache hit, means we can quickly retrieve the data from the cache to the registers. If it's a cache miss, it means we have to go to the main memory, or sometimes go to the hard disk to retrieve the data, because cache doesn't have that data, right? So cache also have multiple layers. There's a hierarchy for cache. Usually, L1 cache is closest to the registers. And sometimes they are divided into the code cache and data cache, depends on the architecture. Then there is L2 cache, L3 cache. They are usually unified, which means you store data and code in them. You don't separate, this is a L1. You don't separate this is a data cache, this is a code cache. And L2, L3 cache sometimes are also shared among CPU cores. And L1 cache usually is specific to a core. So this is a very old picture of a CPU. This is probably a 20 or 30 years old CPU. And as you can see, this is the CPU part. And it has the load store. So this is a RISC architecture CPU. There is execution unit, very small here. The fetching part, very small. The store node part, also store, very small. A floating pointer unit, memory control unit, all those areas are very small. The majority of the CPU is actually the cache. So you can see this L2 cache is already like 60 or 55% of the whole die here. And then we have a level 1 cache, which is the instruction cache here and data cache here. They take another like 8% of the whole CPU. So for the whole CPU, the cache is actually takes the majority of the space. And this is a newer CPU, but still 20 years old, Intel Pentium 4 CPU, and this is a CPU I used to play video games on. And you can see this CPU, there is a L2 cache, another L2 cache. Somewhere here we can say TLB as well. Here we have a TLB. TLB in your operating system class, you probably remember that's, does anyone remember what is TLB? Exactly. So this is because the memory translation is very slow. So because the memory table is stored on the main memory. So to translate any virtual address to physical address, technically you have to go to the main memory to walk through that table to translate virtual address to physical address. That's very slow. That's why we also have a cache for that. And the TLB is translation lookup buffer is the cache to store the recently translated virtual addresses. You probably see other, so here we have a MMX, that's multimedia part for Intel CPU long time ago. There may be other caches as well. So this is a more recent CPU. This is an 8-core CPU. So this is the core part. And you can see that all of those 8 cores, they actually share the L3 cache. So all the cores are collected to the L3 cache. This actually has some security implications. So in Amazon Cloud, you and someone else may run different virtual machines on the same physical CPU, and your virtual machine may be run on the one core, the other guy run on another core. However, they're not separated. They are physically collected. They share the L3 cache. So when your program do something, the CPU will bring your data to the L3 cache. And the other guys, they can infer what of your data has been brought into the L3 cache and to infer what you have done. So that's called the side cache, side channel attack. You can see this is the memory controller part, and each core, they have their own L1 and L2 cache in this case. So some basic concept here before we talk about cache side channel attack. The very first concept is called a cache line. Some papers also call it cache block. Basically, this is the minimum unit of information that can be either present or not present in a cache. So the smallest unit we have in memory is 1 byte, right? You cannot store something, say, I just want to store 1 bit. From information theoretical point of view, the smallest is 1 bit. However, the CPU we use, the memory we use, do not really give an option to store 1 bit. That's why even if you have a Boolean variable, you never store that was a 1 bit. You just use it an integer or a char, because hardware doesn't support directly access for 1 bit. So it will be the same speed anyway, even though you are wasting some space. For cache, most modern Intel and ARM CPUs, the smallest unit is not even 1 byte, is 64 byte. And another concept is called n-way set associative cache. So most of the cache we're using right now, they are n-way. N is a number, which different cache will have a different number. But anyway, there's an n-way set associative cache. What does that mean? It means any given block or line, which means 64 bytes in this case, any given 64 bytes in the main memory, they may be cached in any of the n cache lines in one cache set. We're going to explain those concepts later. So which means when you bring some data from the main memory to the cache, there is more than one place you can bring the data to the cache. So for an n-way set associative cache, we use a 32-bit machine as example. So here, let's say this is the address of a memory location. This is a 32-bit memory location, memory address. And the higher bits from 31 to 13 bits, that's how many? 19 or 20 bits. That's 19 bits. So those 19 bits are the higher 19 bits of the address. They are used something we call tag. Then the middle 12 to 6 bit, that's 7 bits in total, is used for something we call a set. Then the last 6 bits is used for offset. So why the last 6 bits? Because we said that because every cache line has 64 bytes, and the 6 bit represents 64 bytes, 2 to the power of 6, which is 64. So those represent the offset in one cache line. So this is basically a 4-way set associative data cache, and each one has 64 bytes per line. And how many lines of sets is determined by this part, because it has 7 bits for write. 7 bit means 2 to the power of 7, which is 128 sets. So this is basically how the cache looks like. This is a 4-way cache, which means there are 4 columns. There are 4 ways. Then in each column, there are 128 sets from 0 to 127. And each of them is called a cache line, which is 64 bytes. Then if we have some data, 64 bytes, we want to store from memory to the cache, how many ways we can store that? There are 4 ways, means we can store them in each of them. So there are 4 different ways to store that. Which means, however, they have to be stored at that index or that set. That cannot be changed, which is determined by this part. So that 64 bytes can store here, 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 those 4 places. It cannot be stored here. Okay. So what do we actually store there? Obviously, we store the data, which is 64 bytes. We also store a valid tag there, a valid bit there, basically to tell whether what we store here is valid or not. We also store the tag part, which is this, 19 bits. Then we store the data itself. We also have usually we also have a dirty bit to tell if the data in the cache has been updated, but it hasn't been updated back to the main memory. So it means this is dirty. The CPU has updated this cache. However, it's not consistent with the main memory yet. Okay. So the reason we want to have this is sometimes you update some data, we don't really want to push that data back to the main memory because it's too slow. We just push that data in the cache. When we need it later, we load from the cache. So we don't need to put that into the main memory. Another concept is called congruent addresses. So we already know that each memory address maps to one of those cache sets, right? However, many different memory addresses, they can map to the same cache sets, which means they can be placed at the same cache line. And those addresses are called the congruent addresses. And those data in those addresses, they basically compete for the same cache lines within the same sets. And we only have limited number of ways. So when we bring new data in, we may not have an empty cache line available. Then we need to decide how we evict existing ones to make space for the new data. There are several algorithms to do that. Most ARM CPUs, like your phones, they just use a random algorithm. A random algorithm is easier to implement. Then some more complicated CPUs, they use least recently used algorithm or least frequently used algorithm. So think about that. If you use least frequently used, you need to remember this memory location, how many times you used it recently. That means more storage there. Okay, now we can move to the core part of today's class is the cache side channel attack. So side cache channel attack utilize the time differences between a cache hit and a cache miss to infer whether specific code data has been accessed recently. Here I have use ARM as an example. Now let's say we have 2 registers. We have R0 and R1. And R0, we have a value 3000 in hex. And that R0 is the memory location of some data. And in the main memory, we have some data in the memory, and those are the locations. So the instruction here we have is load from memory location R0 to R1 register. So this is basically a move instruction in Intel. You move something from memory to register, and that memory location is in R0. So from what you learned in this class, from what you learned in assembly language, you will simply assume that when you execute this instruction, the data at this memory location is noded to the register, right? However, that is a simplified view of this. What under hood is actually much more complicated than this. What under hood is we have the cache between register and memory. So when you execute this instruction, the CPU does not directly load from that memory location to the register because it's very slow. The CPU wants to run faster. So how does the CPU do this? The CPU will first check the cache. Ask the cache if you have the data at that memory location already. If the cache has that, this is called a cache hit, then the data is directly brought from cache to the register. There's no communication to the main memory. If it is not, then the data will be bring from memory to the cache first, then to the register. That's how it works. That's why it's faster. So, if we can measure the time, how long this instruction was executed. So because of that, this instruction, the execution time for it may be different, right? If the data is already in cache, it will be super fast. If the data is not in cache, this instruction will be very slow. So if we can accurately measure the time before we execute the instruction and after, how long does it take, then we can infer whether that data is already in cache or not. If that data is shared between many different processes, it means we can infer what other processes has been doing. If that data is shared among different virtual machines, it means we can guess what other virtual machines are doing. So over all of those years, many people have proposed many attack primitives to utilize this cache side channel. Actually, I also have a paper proposed approach to this. We call it prime and count. I didn't put it in the slides. So those are the basic 5 approaches proposed in the last 25 years. They all have very catchy names like evict plus time, prime plus probe, flash flash, flash reload, evict flash. So the names are very catchy, but it doesn't really mean those attacks only take 2 steps. Sometimes a little bit more complicated. So the evict time is probably the first approach proposed. It was proposed in 2005, like almost 20 years ago. However, this area has been making progress, amazing progress in the last 28 years. 20 years ago, they have the very first approach. People saying, what can you do with this? And now you can do all kinds of attack with this. So the evict and time approach is very simple. 3 steps. You first measure the execution time of a victim program. Then you try to evict a specific cache set. Then you measure the execution time of a victim program again. Then by telling the difference, you can know the victim program has been using what cache set. And by using what cache set, you can infer what memory locations the victim program has been using. And this has been used to demonstrate to steal crypto keys from AES. Let's say you have 2 processes running on the same computer, let's say Windows or Linux, whatever. Then one of the processes is a web server, and that web server will use AES to encrypt the communications. Then you, as a user on the same program, computer, you can run arbitrary application program. You cannot run kernel modules there. You don't need kernel privilege. You just run another application on the same program, on the same computer, same operating system. Then your application will also use the OpenSSL crypto library, because you are not going to develop your own library. And that library will be shared among different processes, including that web server you're attacking and your program, right? So that's basically how operating system works. We share dynamic libraries. Then you can use this approach to infer the web server, what kind of memory addresses the web server has been accessing. And you can look at your program, what those addresses are. They could be S boxes in the AES implementation. And you can check what S box entries has been used and use that to infer what are the crypto keys. So another approach is called prime and probe. So prime basically means get prepared. Then you do some measurement. So in this approach, let's say the attacker has address space, victim running on the same computer. Then the first step, the attacker occupy a full set of the cache. So how does the attacker do that? The attacker just trying to access some congruent memory addresses, different congruent memory addresses, and the CPU will try to bring the data in those addresses into the cache, and attacker try to fill the whole cache set. Then the victim program will run. The victim program will bring its own data into the cache, and some of them could be congruent addresses as the attacker has prepared, which means some of those attackers' data will be replaced by the victim's data. After that, the attacker will access all of those congruent addresses again. However, it will measure how long does it take to get this address, to get those data. So if some of the data come back very slow, which means those data has been replaced by the victim's data, then you can infer what data the victim has been using. Flash reload, similar idea. So we know that a memory block is cached. Then the attacker first flush this memory block out of the cache. And could be done by some special instructions. Sometimes it's done just by accessing memory. This one in particular, it requires a special instruction. Not all architectures provide this instruction, and not all architecture provide those instructions for applications. But Intel, they have the instruction CL flush, just a cache flush. Yeah, that instruction actually is available for applications. It's not a privileged instruction. Then the attacker can flush this memory out. Then if the victim accesses this block again, it will be brought back to the cache. The attacker measure again whether the victim has been using that. Okay. So in this class, we have several examples, but those examples, I didn't develop those examples. Instead, they were developed by a professor from Syracuse. They developed many examples for challenges for security classes, from software security to network security. We don't use any of their software security challenges, as our software security challenges is much more advanced. However, I didn't develop cache challenges, so he has several. So what we are going to do is each of you will run those on your own computer, because they do not necessarily work on our server. For the homework, you're going to do this. You just need to honestly document what happens, because sometimes it doesn't work. CPUs has been deployed some some kind of defense mechanisms in the last 6-7 years to defeat cache side of channel attack. But let's take a look at the source code here. So here, this is one process. We have a huge array here, which is 10 pages. One page is 4K here. We have 10 pages of arrays. And in the main function, we are going to initialize the very first byte of each page. Then we try to flush all of them out of we try to flush. So when we do this access, we're assigning 1 to that memory location, right? So under the hood, what happens is all of them, they probably is brought into the cache. Usually there is no direct way for us to measure the cache. We can only use the side channel way to measure. There's no instruction. There's no instructions to say, hey, I want to say the cache value at this location. No instruction to do that. Some very advanced debuggers has that, but most CPUs don't have that. Then we flash the array from the cache, and here we use a special instruction to do that. In Intel, there is an instruction for you to do that. Yeah, it's called a CL flush. Then we access some of the array atoms. We do not simply read that. We write something to it, write 200 and 200 to that, which means those two locations, they probably will be brought back to cache again. After that, we just measure if this is the case. We try to read all of those 10 pages, the very first byte of the 10 page, and we measure how long does it take for us to read those 10 items. The theory here is probably reading that page 2 and page 8 data from there. It will cost much less time than reading other pages, because 2 and 8, they are probably in the cache, right? So I think we have this on our server. Let's see if it works. Let's say if we have a source code here, because the source code may be different. Oh, yeah, we have a code repo here. So here we're using 3 and 7 here, you can see. Then let's run this one. Cache. Okay, we run this twice. Let's say if they are really different. 3, they are actually quite different. For the first run, you can see. The page 1 is 400 cycles. Page 1, 500 cycles. Page 3, 240. It's half of that time. Then page 7, 238, right? So the second run, the page 0 is faster. However, 3 is still faster, much faster than average. 7 is faster. So you can't tell the difference. Oh, this one is even better. It's 252. Oh, this one, the first one is 5,000 CPU cycles. Then this one is 200 CPU cycles. So you can see that by measuring the CPU cycles, you can infer what is already in the cache. Even though this is a black box for us, we don't know exactly how the cache is implemented. We don't know exactly what policy to use. You can only find some public document from Intel which do not tell you the full story, but you can get some information out of that, okay? A lot of randomness there, but still some information. So that's basically the first nap, and you are going to do this on your own computer. No matter it works a lot, so you are going to change this program multiple times and to see if it works. So this is an old screenshot from my computer, and you can see that if you do a LS CPU, then you can get what CPU you are using, how many, so what is the size of your cache. So this is my old laptop. I have 48K L1 data cache, 32K L1 instruction cache, and L2 and L3 are bigger, 500K or 8,000K cache. So let's see if we can do this on the server. Yeah, if we do on the server, you can say, I spend a lot of time on the server, so you can say the L3 is big. We actually have GB of L3 cache here. We spent almost 20K on the server several years ago. Yeah. So next class, we are going to talk about two infamous or famous attacks called the Meltdown and Spectrum. And before that, I will give you a little bit basics. So all of those attacks are based on side channel, and they rely on cache side channel attack. And Meltdown allows attackers to read arbitrary physical memory. Here, we're talking about kernel memory from any applications. So for all the classes, OS classes, you learned is if you are running an application, then the kernel memory is isolated from the application. The application will not be able to read that. That is what the CPU, the manufacturers have been doing for 5 or 6 or even longer decades. However, 5 or 6 years ago, people find out that those defense actually can be compromised by using side channel attack, including cache side channel attack. So Meltdown uses a CPU optimization feature called out of order instruction execution. Then try to send back the data using cache side channel as a covert channel. This has been patched on Linux, not on the CPU level, but on the software level. CPU level is really hard to fix. If you already have a shipped CPU, how do you fix that? Very difficult. So a lot of defense were actually proposed at the software layer. So a lot of those attacks, so why they are called side channel? Do you guys understand the meaning of side channel? Yeah, so side channel means it's not a direct channel. You cannot directly measure or view the content in your cache, but somehow through some timing information you can guess. There could be other side channels like temperature, like electronic magnetic waves, whatever, right? So since the CPU manufacturers want to make their CPU faster, they brings all kinds of optimizations there to make the program run faster. And fast or not fast is a timing channel, and that timing channel can be used for attacks. So let's say we have a CPU and has this kind of pipeline. This CPU has 5 stages. So F is fetch, try to fetch the instruction from the memory, then decode this instruction. Then there are execution modules to execute different instructions. Some of the instructions takes more cycles to execute. Some of them only take one cycle, for example this one. And it's simple, take one cycle. This one multiply integers take 4 cycles. Then float pointer multiplication may take even more cycles. After that, it's going to write back to the memory or write back to the register. So the left-hand side, we have some instructions. And the first instruction, we multiply 2 registers, R1 and R2, and put the value into R3. The second instruction, we add R0 to R3, then put the value back to R3. After that, we put R7, R6, add them together to R1, then multiply them together. So then the second part of the program, this is another piece of program. The first instruction, load from memory. The memory address is R1. Load that to register R3. Then add R1, R3 together. Then the other 3 instructions are basically the same as the previous piece of code. So the interesting part here is because the data dependency here, you can say the second instruction here, use the data in R3. So the second instruction has to wait for the first instruction to finish. Otherwise, it cannot execute because it doesn't have the data you need. Here, the same thing. So to execute the second instruction, you have to execute the first instruction first. However, it's not always the case. Many of those instructions, they are kind of independent to each other. To execute the 5th instruction, you don't really need the data of the 3rd instruction. The 5th instruction can even be executed before the 3rd instruction, and the result will still be the same. So this approach is implemented in all of our CPUs now, and this is called the out-of-order execution. And because of this, we can execute programs faster. Let's say this piece of code, the first instruction, we fetch. When we decode, then we execute this. And after the first instruction, we cannot execute the second one, right? So the second one has to wait here. However, the 3rd instruction doesn't have anything to do with the previous 2 instructions. It's not using data from the previous 2 instructions. So one way, the old way of implement CPU is if the second instruction is get stuck here, then all other instructions after that also need to wait and get stuck there. And if we use that approach, you can say we are taking maybe 20 cycles to execute these 5 instructions. So each column here is 1 cycle. And each box here means which module, which stage of the pipeline we are executing which instruction. So here means at the very first cycle, we are fetching the first instruction. The second cycle, we are decoding the first instruction and fetching the second instruction. So the whole thing, the x-axis here, tells us how long it takes to execute those 5 instructions. So it's like almost 20 cycles. So, however, because those 3 instructions are not related to the first instructions, the second instruction here has to wait for the first instruction. It has to wait. It needs the data. However, the 3rd instruction doesn't have to wait. So in the 4th cycle, we do not, the third instruction doesn't wait. The third instruction keep getting decoded and executed, and it can be even right back to the registers. So you can see that by using the approach, those 4 instructions, we saved 4 cycles. If this whole thing is 20 cycles, we actually saved 20% to make the CPU 20% faster. And we're not adding anything to the CPU. It's just using different hardware algorithm. So the CPU will not get more expensive by doing this, but it will be 20% faster. However, like many other things, when people design things, they only want to make it work or make it faster. They don't think about the security implementation of that. And this piece of code explains how we can utilize this to steal things from the kernel, which is unthinkable before. So this piece of code is a kernel module, which means in your when you do this experiment, you are trying to load this into the kernel. And you are going to embed some secret in this and try to steal this. And the secret here is just a string, 8 characters. And as a kernel module, how many of you developed a Linux kernel module before? Nope? Okay. So the kernel module doesn't really have a main function. It will be loaded into a kernel address space, and you need to tell the kernel what is the entry point. And this module init is the entry point, and also module exit is the exit function. When the kernel exits, the kernel always calls this function. So in this case, the entry point is test proc init here. Then this function will use print k to print out some kernel message to a buffer. So in the kernel, you don't have printf. So you have been using printf, but printf is a C library function. The kernel doesn't have a C library. The kernel doesn't use C library. Okay, so that's why the kernel doesn't have printf, but there is a printk function. It's almost equivalent to printf. This doesn't print to the terminal. It's usually print to a kernel buffer, equivalent to a log somewhere. Then the kernel will get some memory using malloc. Here we're using vmalloc, which is a kernel heap function. Then after that, create a file on the proc file system, so the user program can interact with this kernel module. Then you can interact with this kernel module with an open system call. So there are many kernel modules in your Linux, and they have been loaded in the kernel, but usually they have the same interface. The interface is just the open, read, close. Those are interface. Even though there are many different modules developed by different people, different companies, the interface are the same. Those system call interface, like open, close. Now here we have how the open system call is implemented on this module. Then that maps to the test proc open, which is this part. Then it will just open a file, then return the value. And there is also a read call where try to copy the secret from the kernel memory to another kernel memory. Okay? So this memory copy happens in the kernel. It's not copying from the kernel to the user space. However, because of this copy, that memory location is read, and data is brought into the cache. And the attacker will utilize that to steal the data. the copy. So there is no software vulnerability in this piece of code. Okay, so different from what we started the whole semester. We're not talking about software vulnerabilities. No software vulnerability. It's the design of the CPU itself is going to leak information. Another attack is called spectral, and it relies on speculative execution. This is also a CPU feature that has been introduced in the last 20 years. So the processor, the CPU, can preserve its current register state and make a prediction as to the program path it will follow, and speculatively execute the instructions along the path. So if the prediction turns out to be correct, then the result of the speculative execution are committed, are used, and this will yield a great performance advantage. Otherwise, if the CPU finds out that it actually took the wrong path, then it will just revert the register states. However, people find out that Intel CPUs and many other companies, they only revert the register state. They didn't revert the cache state. So the result was actually stored in the cache. The speculative execution on modern CPUs can run hundreds of instructions ahead. Let's take one. This is related to the branch prediction, and let's say one example here. This is a very simple say predicate. We have if x is smaller than a global variable. If x is smaller than that value, then we are going to access arrays, use that index x times this page number, this value in another array, and bring this to the global variable, to another variable y, right? So there are basically several cases. If x is inbound, if x is really smaller than this, then let me back up a little bit. So when you look at this piece of code, you only think about to execute this faithfully. But CPU doesn't do that because CPU wants to do it faster. So CPU will actually make predictions. Let's say this x compares the value of x with the value of array one size. Takes a long time. Takes a very long time. Then if we faithfully execute this piece of code, then we will just get stuck here, waiting for the results. When x, whether x is greater or less than this value, returns. However, the CPU feel waiting there is wasting of CPU cycles. So before the value of this is returned, the CPU will actually guess whether x is smaller than this or bigger than this. The CPU will guess that. So in this case, if we let the CPU guess x is smaller than this, then the CPU will keep executing this piece of statement. But later, after CPU then store that information internally at the CPU. However, later CPU find out that x is actually greater than array one size. The CPU will just get rid of the value, the results of this statement. Okay? So ideally, that works. The problem is previous CPU designs, they only revert the register values. They do not revert the cache values. So by looking at this, you can say, even if y's value can be reverted, However, some value was already brought into the cache. Then we use cache side channel attack we talked before to infer the result of this. So the implementation of this is this piece of instruction may not be, should not be executed. This should never be executed. We don't have the privilege, attacker, we don't have the privilege to execute that. However, we trick the CPU to execute that because CPU wants to be faster. And after CPU executes that, CPU later realizes it should not execute that, then clean up the registers. However, the CPU doesn't clean up the cache. Then we steal the search information from the cache to get what we want. So, very fancy attack. So when this kind of attack came out 5-6 years ago, you can imagine it's a huge shock. Like decades of research, decades of deployment turns out to be wrong, right? There are actually different versions of Spectral. There is also an indirect branch version of this. And the interesting part of this is, how does CPU guess? How does CPU guess if X is smaller than array size? You can actually train the CPU. So you can have a piece of code before this, and that piece of code X is always smaller than array 1. So CPU somehow remembers that. Then CPU guess, oh, it's more likely X will be smaller than array 1 size. However, when you really do the attack, that number is, X is actually greater than size 1. Okay, so those are the high-level idea of those two attacks. Next class, we will say a little bit more detail of this. Meltdown doesn't use branch prediction. It only uses out-of-order execution. Meltdown exploits vulnerabilities specific to Intel and some ARM CPUs. And Meltdown can access kernel memory from user space. There has been a lot of research talking about how to mitigate Meltdown at software level. And also, let's say if this CPU has that, let's say, here, you can say, when we do LS CPU, it tells us vulnerability Meltdown, vulnerability Spectral, vulnerability version 1, version 2. So you can say here, Meltdown not affected. So this CPU is not vulnerable to Meltdown. However, Spectral 1, 2, it's vulnerable. However, it is mitigated somehow using some approaches. Then after that, there are many other attacks you can see. Most of them were introduced after Meltdown and Spectral. So they find a new world of attacks. After you understand the high level, I guess you can feel how complicated this attack is. But very, very cool stuff. Okay, so let's take a look at the homework this week. Today is 4th. Homework this week is simple. You just need to capture the flag of heap overflow 1 and 2. Then after that, you do a LS CPU on your own computer, and then just Google the CPU and try to figure out the cache size and how many levels of cache you have on your own computer. Okay. For the homework 12, I will try to finish it today, so then I can have an estimation how many days I want to give you guys extension. Probably at least give you 4 or 5 days. Very likely I'm going to to ask you guys to head in both homework 12 and homework 13 at the same time next week. Yeah. I will try to give you some hints tonight. Okay, cool. So next class, we talk about Meltdown Spectral more. Then I'm going to talk about what is beyond what we learned from this class. So that is basically some ideas I had for my advanced software security class, which I never had a chance to offer here. Then we are going to watch a video together, which is a keynote speech from CCS several years ago, talking about a professor, Taishu from Georgia Tech, summarized the software security in the last 2 decades and where he believes software security is going. A large part of that video, he's just advocating Rust. How many of you heard of Rust or used Rust? Okay. So large part of the video, he's talking about Rust. Obviously, Rust also have many issues. Actually, last week, I saw a paper talking about the Rust code is still vulnerable to Spectral. Yeah. So, I think he's talking about Rust and Spectral published in CCS this year. Cool. Any questions? Okay, good. See you guys next week.
I had a question. So,
Yeah.
looking at your server, basically, it said it has 1.5 gig of L3 cache. How is that possible? I mean, is it because no consumer CPU, even Threadripper and Epic offers like.
So, first of all, we have probably 200 CPUs on that server.
Oh,
Yeah,
okay.
it's not
Unified,
just
okay.
it's not just one big CPU. Yeah.
Oh, okay, got it.
Yeah, so that server probably have 200 gigabyte of memory,
Oh, okay.
at least 100 CPUs.
Oh,
Yeah, I
that
think
makes
so.
sense.
Yeah,
Yeah.
yeah. So combine them together. I don't know after we install virtual machine everything how you calculate that.
Oh, okay.
Yeah, I don't know the details.
And for the ROP2, so I tried a few things. One, I tried to put a shell code in environment variable. It didn't
What
take.
do you mean by share code?
The open that we use for buffer overflow, right?
No.
It didn't work.
The share code doesn't work because the stack is
Not executable, exactly.
Yeah.
I figured that later, and then I
Yeah.
tried using some ROP gadgets to kind of call open, but
Yes.
then the problem was that
Yes.
once the variables to call open, I need to pass the file descriptor path.
Yes.
I can't remove them from the stack afterwards because when open returns, it'll again find the first value to be present.
Yes. So